So the next thing we're going to look at, which is actually really, really important, is this question of to what extent does water actually break up into ions like this. You could investigate that experimentally by taking completely pure water and just asking the question, does it contain any ions? And you could test for that by measuring its conductivity. And what you find is that pure water has extremely low conductivity, but it's not zero, because a small proportion, a very small proportion of water molecules do actually break up and produce H+ ions and OH- ions. So this equilibrium lies far over to the left. The overwhelming majority of water molecules are just that, but this tiny proportion of them break up into ions. So if we think about that, it's an equilibrium, so we could write a Kc down, an equilibrium constant, which, following the normal rules, would just be H+ times OH- divided by the concentration of H2O. But when you learnt about Kc earlier on, we learnt that when you have a reactant which is also the solvent, and usually that will mean water in the examples that you're going to come across, you generally leave it out of the Kc expression, because the concentration of the solvent will be so much higher than that of the stuff dissolved in it generally. It's a reasonable approximation to treat that as a constant. So what you could do is to just rearrange that expression and say Kc times H2O is equal to H+ times OH-. Okay, so we're just rearranging that expression, and what we're saying is that Kc is a constant, provided the temperature is the same, and this is roughly a constant. So, to a good approximation, we can say that that term is constant, and we're going to give it a special name, which is Kw. Okay, Kw is, put in words, sometimes it's called the ionic product of water. And you can see that it's just equal to H+ times OH-. So that doesn't look like an equilibrium constant, but it is, because you can see that we've just simplified it by taking that term out of it. So it has all the properties of equilibrium constants. In other words, it's truly constant except when the temperature changes. And it's an incredibly useful number, as we'll see. So if you look on your data sheets, you can find the value of that, and it tells you it's 1.00 times 10 to the minus 14. The units are moles per dm cubed squared, so mole squared dm to the minus 6 at 25 degrees C. And it will change when we change the temperature. But as I say, that number is on your data sheet, and you'll find that it's very useful, not just for figuring out what the pH of water is, but also, as we'll see, for figuring out what the pH of alkaline solutions is going to be. Okay, so one of the things that's nice to do, just because it shows that things work out as you might expect, but also because it's potentially quite an important thing to do, is to use that Kw that we've just learnt about to deduce what the pH of pure water should be. So we've got that Kw is equal to H+ times OH-. And remember, if we're talking about pure water, the only way you're going to have any of this or any of that in the solution is as a result of the ionization. Okay, because you haven't got anything else in the solution, you haven't added any of this or any of that. And of course the consequence of that is that these two concentrations must be the same, because every time a water molecule falls apart you form one of those and one of those, so you must have equal numbers of those. So we can therefore say that Kw therefore equals H+ squared. Only for pure water, not if you've added any acid or alkali to it. Okay, but for pure water only, that must be true, because if this concentration is the same as that one, multiplying them together will give you the same value as just squaring the H plus concentration. Okay, but it's really important that you remember that that's a special case. Only apply it to pure water. Whatever you do, don't write that down for a solution that you've actually added some acid to or added some alkali to. And then we're almost there, because we can therefore take the square root of both sides and get that the square root of Kw therefore is equal to the H plus concentration. And we know that at 25 degrees C, that's 1.00 times 10 to the minus 14 mole squared dm to the minus 6. So we can therefore say the square root of 1.00 times 10 to the minus 14 is equal to the H plus concentration at 25 degrees C. And the square root of that is 1.00 times 10 to the minus 7 moles per dm cubed. And lo and behold, if we calculate pH, which is minus log to the base 10 of the H plus concentration, and you take minus log of that number, you get 7.00, which is reassuring. So that's one of the things that you can do usefully with Kw. You might think, well, okay, now that you've seen it, it's not something you'd ever want to do again. But of course you might, because it's only equal to that value at 25 degrees C. When you change the temperature, the value of the equilibrium constant changes, and consequently the pH changes. So what you find is if you go up to high temperature, the equilibrium, when you go to high temperature, shifts to the right. You get more ionization at higher temperature, so the concentrations of these things increase, and that means that Kw gets bigger, and that means that the pH gets smaller. So if you go up to 100 degrees C, you find that the pH of water is not 7, it's somewhere around 6.1. That doesn't mean water's acidic, because it's still neutral, because you've still got equal concentrations of these, but the pH isn't 7. So you've got to remember that number isn't some sort of magic number that's set in stone, it just happens to be the pH at 25 degrees C. We can use the existence of this equilibrium and the equilibrium constant Kw that goes with it in order to figure out what the pH of an alkaline solution is. Because if you think about it, pH requires us to know what H plus is, and we can easily rearrange this equation to get H plus is equal to Kw divided by OH minus. Okay, so just rearranging the definition of Kw. So what that means is that if we know what the concentration of OH minus is in our alkali, so if it's 2 molar sodium hydroxide's fully ionized, so OH minus will be 2 moles per dm cubed, then we can just take our value of Kw from the datasheet, divide it by the OH minus concentration, and that gives us the H plus concentration. So if we look at an example of that, we can sort of put that in some kind of perspective. So suppose we use that example of 2.0 mole per dm cubed sodium hydroxide. So that means that the OH minus concentration is 2.0 moles per dm cubed, because that's a ionic compound, so when you dissolve it in water it just breaks up completely into its separate ions. So we know what the OH minus concentration is, so we can therefore get that H plus is equal to Kw over OH minus, which is 1.00 times 10 to the minus 14 divided by 2.00, which is 5.00 times 10 to the minus 15 moles per dm cubed. So what that's telling us is that the concentration of H plus is tiny, 5 times 10 to the minus 15, so incredibly low concentration, but it's not 0, because this is a reversible reaction, even in a solution of, quite concentrated solution of alkali, you still have a tiny but non-zero amount of H+. And that's what the equilibrium constant gives you. So because that's a very tiny concentration of H+, pH, which is, remember, minus log of H+, is going to be quite high. So that's our definition of pH. We plug that number into there and we get 14.3 is the pH. Which makes sense. We tend to think of pH 14 as the top end of the pH range. That's actually the pH of 1 mole per dm cubed OH-. So if you've got a higher than 1 mole per dm cubed concentration, you'll get a pH above 14. But obviously it's limited by solubility. You can't get an OH- concentration of, say, 70 moles per dm cubed, because no hydroxide is that soluble. So it'll go a little bit above 14, but not very much. If we look at another example of that, so let's take barium hydroxide this time, at 0.085 moles per dm cubed. We've got to be a bit careful this time, because that's the concentration of the compound. But of course, because of the formula, each mole of that compound contains 2 moles of OH-. So you can't ignore that 2 there. So the formula implies each mole of BaOH2 contains 2 moles of OH-. So if the concentration of BaOH2 is 0.085 moles per dm cubed, then the concentration of OH-, again, like sodium hydroxide, it's going to be completely ionized. Ionic compounds, remember, break up completely into their separate ions in aqueous solution. So the OH- concentration will be 2 times 0.0850, which is 0.17 moles per dm cubed. And then it's just the same as the previous one. So we take this and rearrange it, our Kw expression, to get H+ is equal to Kw divided by OH-, which is 1.00 times 10 to the minus 14 divided by 0.170, which comes to 5.88 times 10 to the minus 14 moles per dm cubed is the H+ concentration. And then pH is minus log of that number, which comes out as 13.2. Which again is what we would expect. So the concentration is less than 1 mole per dm cubed this time, so we expect the pH to be lower than 14, and that looks about right. So that's just a slight extra complication. Watch out with formulae that have more than 1 OH- in them. Of course, you also need to be able to go back the other way. If it gives you the pH of an alkaline solution, you need to be able to work out what the concentration of OH- is, and therefore what the concentration of the alkali that's in there is. So the way to do that is, first of all, to do like we did with acids, to convert the pH into H+ concentration. So our starting point is to remember that H+ is equal to 10 to the minus pH. So that's the inverse log of minus the pH, which is 10 to the power minus 12.9. And that works out as 1.259 times 10 to the minus 13 moles per dm cubed. So that's the H+ concentration, but we want to know what the OH- concentration is. So again, we use this and just rearrange it to get OH- is equal to Kw divided by H+, which is 1 times 10 to the minus 14 divided by this number that we've just calculated, 1.259 times 10 to the minus 13 moles per dm cubed. and that works out as 0.0794 moles per dm cubed. So that's the OH minus concentration, but as we've said, these are ionic compounds. They're completely broken up into ions, so each mole of lithium hydroxide will give you a mole of hydroxide ions in solution, and therefore we can say that the concentration of LiOH in this case is the same as the concentration of OH minus, which is 0.0794 moles per dm cubed. Okay, so now you can deal with strong acids, you can deal with water, and you can deal with strong bases. What we go to next is to look at weak acids, which is really a much more important application of pH, really, in terms of where it's used in real life than the things we've done so far.